Hello, in Module 5 we will do some exercises on reference frame and pulse width modulation of converters. In the first part we are asked to open reference frame Simulink file and run the model and see the signals in the scopes. So let's open the file. Here you can see there are two subsystems for ABC to alpha beta and ABC to DQ transformations. One point which is good to notice is here we don't need any power GUI block. You can understand the reason by reading the description and help of power GUI model. So in this Simulink model we don't have any power system component, so we don't need to insert power GUI. Also, as always, you can see the model properties, initialization functions, info, and other information that might be of your interest. Now let's run the Simulink model and open the ABC to alpha beta and then again to ABC transformation and see the signals. Here at the top we have ABC input, and at the bottom we see the output ABC signals. If we zoom in, we can see that input ABC and output ABC are equal to each other without any phase shifts or amplitude change between them. That is reasonable because in the model that we have, there is no component or delay in between two transformations. So the output of ABC to alpha beta transformation is going directly to alpha beta to ABC. Concerning the alpha beta signals, which is the graph in the middle, we can see that the alpha signal is in a line with phase A, and there is a 90-degree phase shift between alpha and beta signals. To better interpret these signals, we can go to the help of this block and see how it is implemented. Here, if we look at the graph, we can see alpha axis is aligned with A axis, which means that alpha signal will be aligned with phase A signal, and for the beta signal, we can see that beta signal is between phase A or A axis and B axis, and there is a 90-degree phase shift between alpha and beta signal. Based on this, if we look at the signals, we see beta signal is really between signal of phase A and phase B, and there is a 90-degree phase shift between alpha and beta signal. There is a zero signal that we disregard in this case. In the next part, we are asked to uncomment transport delay and run the simulation. At the beginning, there is no output signal because of the transport delay. There is a 180 degrees phase shift between input signal and output signal, which is equivalent to half a cycle, and half a cycle in this case is 10 milliseconds because the frequency of the signals is 50 hertz. The other point is that still alpha signal is in phase with phase A signal, and that is because we are plotting the alpha beta signals before transport delays. It is not asked in the exercise, but you can always play with the time delay here and run the model, see the result and try to interpret the result. That helps to deepen your understanding about this transformation. For example, if we run the model with 20 milliseconds, we can see that except for the beginning, the input and output signal are in phase because 20 milliseconds is one cycle. In the next step, we are asked to do the same with alpha beta to DQ transformations. In this case, there are two multi-port switch. Switch 1 determines the angle which is used for the transformation, while switch 2 determines the signal which is transformed between the reference frames. If you go to the corresponding subsystem, we can see this index signals which goes to the multi-port switch, and the multi-port switch 1 is providing omega t, which is used as the reference angle for DQ transformation, while multiport switch 2 is providing the signal as the input to the transformations. There are two paths in this model. One is showing the ABC to alpha beta transformation, then alpha beta to DQ. But in the other path, we are using another block of MATLAB, which is ABC to DQ directly. The aim of this part of the exercise is to show you that the ABC to DQ transformation is actually a combination of ABC to alpha beta and then alpha beta to DQ transformation. The resultant signals will be similar as we will see in this exercise. The signals for index 1 and index 2 are summarized in table 1, so we can see which signals, and we can compare them with the Simulink model. Here we see, for example, for multiport switch 1, we can see the signals, and for the multiport switch 2, first one is a 50 Hertz signal, second one is a 50 Hertz signal again, but the amplitude is increased. The third one is also 50 Hertz, but there is a phase shift introduced in the signals. And finally, we have the last signal, which is a 60 Hertz signal. Here we just observe the phase A signals because the other signals are the same, except that they are shifted by 120 degree and 240 degree for phase B and phase C respectively. So knowing these things, we can continue the exercise and fill in the table 2 by running the model for different combination of index 1 and index 2. In the first case, both indexes are asked to be set to 1. So let's run the model for this case. The first thing that we can see here is that the input ABC signal and output ABC signal are exactly same to each other, and that is because there is no delay or other component in between the transformations. So we can fill in the table for this case. Here omega t is equal to 0, and also we can copy the VABC input signal from table 1. We just consider phase A, and we know that how the phase B and phase C will look like. The middle graph in this case is DQ signals. So on the left side it is transformed from alpha beta to DQ, and on the right side it is ABC to DQ. Here we can see that D-axis signal is leading the signal of phase A by 90 degree, and also one cycle of this signal takes 20 milliseconds, which means that it is a signal with a frequency of 50 Hertz. Also for the other transformation, which is ABC to DQ transformation, we can see it's exactly same as the other one as we were expecting. So because that alpha beta is already converted from ABC to alpha beta and then alpha beta to DQ. So these two signals are exactly same to each other. Also, we can see that the output ABC signal is exactly same as the input signal in both cases. You can deactivate the other phases to make the comparison easier. So ABC output is equal to ABC input, as we were expecting, because there is no delay in between. One important point to take into account is the setting of this alpha beta to DQ transformation, which if you open the dialog box of this block, you can see that the rotating frame alignment is 90 degree behind phase A, that is why we have this 90 degrees leading of D-axis signal respect to the phase A signal, while the alpha signal is aligned with the phase A signal. So here actually the output of that ABC to alpha beta signal, the that signal is aligned with phase A signal, then because of the setting of this alpha beta to DQ, there is a 90-degree phase shift. Also, the omega t here is 0. The other important point here is the frequency of DQ signal. We can see it's a 50 hertz because omega t is in this case is 0, and if we look into the help of this DQ transformation and see the transformation matrix here, by setting omega t equal to 0, we can see that the matrix will be an identity matrix, which means that u dq is equal to u alpha beta. Also, if we consider the transformation matrix with the setting that we used for the Simulink block, which is 90-degree behind phase A, in this case also the UDQ signals are directly connected to alpha beta signals, and there will be no shifting in the frequency. The frequency of DQ signal in this case is also 50 hertz, and that is very important to notice. So in this case, the omega t is 0, so there is no shift in the frequency. In the next case, we need to set index 1 to 2, which means that omega t will be pi divided by 2 or 90 degree. And the input signal is still the same because index 2 is equal to 1. In this case, we expect that the frequency of DQ is still 50 hertz, but we see a 90-degree phase shift of the DQ signals respect to the previous case because omega t is now 90 degree. It doesn't impact the frequency of DQ signals, but it will introduce a shift in these signals. Here still we see that the output signal is equal to the input signal as is expected because there is no delay in between. For the DQ signals, we can say that D signal or VD is in phase with signal of phase A, and the frequency is again 50 hertz. In the previous case, the phase shift between DQ signals and alpha beta or ABC signals was 90 degree. Now there is no phase shift between them because omega t is now 90 degree and is compensating for that. So let's write it that it is same as the V alpha beta to DQ. So it's easier to follow the table. In the next case, index 1 is equal to 3, which makes omega t like a signal which is rotating with 30 hertz. So in this case, the frequency of our DQ rotating frame is 30 hertz, while the frequency of our input signal is 50 hertz. So we expect that this 50 hertz signal respect to that 30 hertz rotating frame is observed as a signal with a frequency of 20 hertz. By running the simulation, we can see that in this case also output signal is equal to input signal. If we look at the signal, we can see that each cycle of the DQ signals takes 5 milliseconds, which is equivalent to 20 hertz. Same will happen when we use the ABC to DQ signal. We expect that because actually that this VABC to DQ block contains this V alpha beta to DQ. Also, let's use C dot for the product instead of this star. Now, in this case, the main thing is this frequency that we considered. In the last case, we are asked to set index 1 equal to 4, which is equivalent to a reference frame with a frequency of 50 hertz. Now the frequency of the rotating frame is equal to frequency of the input signal, so we expect that the input signal is observed as a signal with a 0 frequency, which is like a DC signals. So let's run the model. As we were expecting, the DQ signals in this case are DC values, and the input and output signals are equal to each other. In this case, so we can fill in the table. VD is equal to 1 and VQ is equal to 0. And it's same for the other transformation, which is the VABC to DQ. And finally, we saw that the output signal is equal to input signal as well. Here, as we discussed, we get the DC signals in DQ frame because the frequency of reference frame is equal to the frequency of input signal. Now let's change the setting of one of the transformation blocks to align with phase A axis and run the model again. Now if you look at the result, we can see still DQ components are DC values, but now the D axis is 0 and Q axis is -1. And this is important to take into account when designing our controllers. But the important point here is that the output signal is 90 degrees shifted respect to the input signal. And that is because we have chosen different alignments for the alpha beta to DQ and the inverse of this transformation, which means the important thing here is to use this similar alignment for both transformation. Now we can see that the input and output signals are aligned with each other, which makes sense because there is no delay in between. So let's bring back the setting to the previous setting and continue the exercise. In the next part, we are asked to make VABC2 as the input to the transformation. In this case, it's 50 Hertz, but the amplitude of the input signal is 1.1. So yeah, we can copy it from table 1. Now the frequency of rotating DQ reference frame and the input signal, both of them is 50 Hz. So we expect to see DC values for D and Q components. The impact of amplitude of this input voltage can be seen on the DQ axis. As you can see that the D axis is equal to 1.1, which is consistent with the amplitude of the input voltage. It's important to note that in this transformation, VD, or the amplitude of the DQ vector, is equal to the amplitude of the input signal, not the RMS value of this signal. This is important when designing the controller and also considering the factors to be used in the controllers and power equations. Now in the next part, we are asked to do the same with the VABC3, which is a 50 Hz signal, but shifted by 60 degree. Here the rotating reference frame is rotating with 50 Hz, and the input signal is shifted by 60 degree. Now if we run the model and see the result, we can see still the DQ components are DC because the frequency of the rotating reference frame is equal to the input signal. The impact of this phase shift is on the DC value of this DQ component. Here in this case, there is a 60-degree phase shift between the input signal and the DQ frame. So that is why we will observe that now Q component has a value of 0.866, which is equivalent to the sine of a 60 degree. As we mentioned, there is this 60 degree between omega t of the reference frame and the phase of the input voltage. So we expect, I guess UQ should be 0.866. Let's check it again. Yes, 0.866 is actually UQ, which is in blue, and the yellow line, which is UD, is 0.5. So let's correct it. If we want to have a VD equal to 1 and VQ equal to 0, the one solution is that we shift our rotating reference frame by 60 degrees so that the input signal is aligned with the rotating reference frame. You can try to add pi divided by 3 to the omega t and see and run the simulation and see the result. And finally, we are asked to run the simulation for when both indexes are at 4. In this case, the input signal will have a frequency of 60 Hz. Now there is a 10 Hz difference between frequency of the rotating reference frame and input signal. So we expect that the DQ components in this case will have a frequency of 10 Hz. After running the model, we can see that the input and output signals are same, but the DQ components has a frequency of 10 Hz, or and in the result we can see half a cycle is 50 milliseconds, or a full cycle is 100 milliseconds, which is equivalent to a frequency of 10 Hz. So we can write it here. The other DQ component is same, and the output signal is equal to the input signal. We have filled up table 2, and we can see the result for all of them. So let's bring it to one page. The conclusion from this table is that the DQ component from both kind of transformations, which is ABC to alpha beta and then alpha beta to DQ, is similar to ABC to DQ, and also the output signals is equal to the input signals because there is no delay or any other component in between. We also saw the impact of amplitude on the DQ components, and also the phase shift when the frequency is same. And finally, we saw again another example for the difference in the frequency of rotating reference frame and input signal. Here we saw that the DQ component has a frequency of 10 Hz, but I will ask you what is the difference between these 10 Hz and the case that the input signal has a frequency of 40 Hz instead of 60 Hz. So in that case also the difference between frequency of reference frame and the input signal is 10 Hz, but the frequency of the input signal is 10 Hz below the rotating reference frame. What do you think is the difference between these two cases? And similarly for the case when the difference in the frequencies is 20 Hz. The next part of this exercise focus on the modulation index of converters. At the beginning, we will do the simulation with average model, which is based on the model that we built in module 2. So you can see it's similar to that module, except that the stop time is infinite. So the simulation will run until we press the stop, and also the setting of the scopes is changed. So it only covers 50 milliseconds of time span. Also, since the simulation is running, it's good to limit the logging data in the logging of the scopes. And you can check it for all the scopes in this model. As always, you can look into the model properties to see what is going on in the callback, and here we can see that the simulation parameters is running at the initialization of the model. We are asked to comment out the grid and also to neglect the current waveforms. You can easily neglect them by commenting out, but I will keep the current signal so we can look into them. In the next part, we are asked to disconnect the control loop of this model and use constant values to dictate the value of UD and UQ. Also, for the frequency, the converter needs to dictate the frequency of the generated voltage, because there is no other voltage source in this model. We disconnected the grid, and we can do so by giving the desired angular frequency and obtain the omega t by integrating this value. This way, the converter is actually working in the grid forming control mode, which is generating voltage and frequency. Even so, there is no voltage and frequency in the grid. We will get to know these grid forming concepts in the future modules. In the next step, we are asked to run the model for different values of UD and UQ. So let's add a scope for observing the voltage, only voltage in one scope. And you can use the previous scope also, but I prefer to have only voltage here. So this is the voltage and current. We can see that both of them are 0 because the reference value of voltage are 0. Let's make it 0.5 per unit as it is asked in the exercise. Now we can see that the generated voltage has an amplitude of 0.5 as well. You can always follow the signals and check the equations and draw the control diagram of this model on a paper to understand why 0.5 per unit of dq voltage gives this voltage with an amplitude of 0.5 per unit. That's good to understand the scaling factors between the transformations. Now we can pause the simulation and see the result. You can see the amplitude is 0.5 per unit, and we can copy it to the document. The good thing about this having the infinite simulation time and using the pause button is that we are skipping this compiling of the model every time that we want to change something in the model. The change can be done only on parameter values in this case, and we cannot change the connection of the components because the model is already compiled based on the connection that we had at the beginning. But still, we can change the parameter values and see the impact on the output voltage. So let's do it for 1 per unit of voltage. and run the model. So we can see the out generated voltage has an amplitude of 1 per unit, which means that it is behaving as we are expecting. And now test it for a 2 per unit of input voltage. The generated voltage has an amplitude of 2 per unit also. So the generated voltage is following the reference signal that we are giving to the model. So next one is 5 per unit. Let's run the model for 5 per unit. Again, the amplitude of output voltage is also 5 per unit, which is consistent with the value of the reference voltage that we are providing. In the last step, we are asked to change it for a very unrealistic case of 1000 per unit voltage. We can see that our converter is generating this high value of voltage. Also, if you look into the other scope, we can see that when voltage is very high, we have some currents. And if in case you are wondering, that is because of the magnetization, resistance, and inductance of the transformer that you can check into the inside the model. Apart from this, the converter is generating whatever voltage we ask from it, which makes sense, but it is not realistic because the in reality converters have some limitations. The point is that in this case we are using this average model of the converter. If you go to the help, you can see how the average model is modeled in the MATLAB, and it is basically modeled as a three-phase voltage source and is generating whatever voltage we are asking from it. You can say that maybe this is a bug in the Simulink model and the non-linearity of the converter can be added to this model, but the purpose of this exercise is to show the non-linear operation of the converters. So we have the other model which is modified based on one of the examples of the MATLAB Simulink library. You can find this model by writing the name of the model in the command window of MATLAB. One R is missing, so let's do it again. Yeah, here is the model. You can read more about this model in the by going to the correspondent page. And also see the model properties, where your file, where this file is located in your system, callbacks, info when it is created, and any other information that you want. If you want to modify this model or any other Simulink example, you can save them as another file. Let's say whatever name you choose and save it, and then do the change that you want. Here we have the modified version of that model, except that the stop time is infinite and the setting of the scopes is modified as well, in addition to removing some parts of this example. Also, you can see that after running the simulation, the scope is open. It's because of the setting of the scope. Now everything is 0. Let's see it for 0.5 per unit of input voltage. Now we can see the output voltage is also 0.5 per unit, as we were expecting. Next, we try the model with 1 per unit of input voltage, and we can observe that the output voltage is also 1 per unit as we are expecting. And next one is for 2 per unit. In this case, we observe that the generated voltage by the converter is not actually 2 per unit, but it's around 1.5 per unit. Now let's continue and run the model for 5 per unit of the input voltage. Now the saturation of the converter is more obvious in this case, and you can see even that the switching of the IGBT switches is reduced respect to the previous cases. And finally, for a reference value of 1000 per unit, we can see that there is actually no switching, and there is only switches between the phases, which are the natural switching of the converter. The previous one, yes, sometimes there are some delays when copying the data of a scope to the clipboard. So here we could see that there was a delay. If you are facing this problem, I recommend that you wait a bit after copying the data so it is loaded actually into your clipboard, and when you paste it, you will have the correct graph. In the next step, we are asked to add a modulation index subsystem to the model. Let's stop the simulation and use the DQ to ABC subsystem for creating the modulation index subsystem. So let's go inside and remove the component we don't need. Put it here. The output signal should be UDQ mode or modulation. And the modulation index subsystem should be something like this, which is basically a Cartesian to polar transformation, and then a polar to Cartesian transformation. We do so we decouple the amplitude and the phase of the UDQ components, and we can limit the amplitude of the reference voltage, keeping the angle of this UD and UQ unchanged. We do so because in the previous case we saw that if the value of reference voltage is high, the converter is saturated and the resultant voltage is distorted. So we are adding this saturation block on the value of reference or on the modulation index to avoid this nonlinear behavior of the converter. Adding this, we are asked to repeat the simulations again. So for 0.5 per unit, in this case, we expect that there is no change, and we are having the 0.5 per unit of voltage, because the saturation lower limit is 0 and the upper limit is above 1. So for 0.5 and 1 per unit of reference voltage, we don't expect any difference respect to the previous model. But when it is a 2 per unit, we can see that the resultant voltage is not 2 per unit, but it is not also distorted. Same will happen for a reference voltage of 5 per unit. So it's not 5 per unit, but it is not distorted, and that is thanks to the saturation that we introduced in the amplitude of modulation index. Even for a voltage reference of 1000, we don't see the distortion in the output voltage. So we need to have this saturation to avoid operating in the nonlinear area of the converter. In the next part of the exercise, we are asked to change the voltage of DC link. So let's make it for 0.5. we can see that for 0.5 the output voltage is also 0.5. When the voltage is 0.9 per unit, the output voltage is also 0.9. For 1 per unit it is 1 per unit. 1.1 per unit of the DC link voltage is reflected on the output voltage also, and leads to 1.1 per unit of the output voltage. Similarly for 1.5 per unit, and actually we can test it for any value of DC voltage that you want, even if it is not asked in the exercise. You can see that the output voltage is generated. We consider the switching model of the converter, but the output voltage is can reach to very high levels. That is because the modulation index in this case is 1 per unit. We are not changing the reference value of UD and UQ, but we are changing the base value of the voltage by changing the voltage of this DC link. So the value of the DC link voltage is reflected on the AC side. So if we change the DC link voltage, we are actually scaling the AC voltage in the same manner. That is why we see the output voltage is increasing without any limit, despite the fact that we introduce the saturation on the modulation index. This can be problematic because the DC link voltage is not considered in our control loop or when calculating the voltage. But before going to that, we can see that the scopes are storing all the signals from the beginning of the simulation. So let's limit the data point to the number of data points which is required for the time span of 50 milliseconds that we are observing. We can see that it's covering very small area, not 50 milliseconds. We need to set the sampling time to TS to make sure that it has a equal sampling time as our simulation time step. We can see that log data is equal to our time span of 50 milliseconds. In the model that you have received in the exercise, we already considered this point in the setting of the scope, but to make sure, just try to check it on the scopes. We are asked to add the impact of DC link voltage measurement in the modulation index. As always, you can do some formatting and then use one of the input for getting the DC link voltage measurement. We saw that if we increase the DC link voltage, the output voltage is increasing, but we want to avoid it. So the solution for that is to divide the modulation index by the DC link voltage, because if our DC link voltage, for example, is 2 per unit, our modulation index needs to be 0.5 per unit to have a AC voltage of 1 per unit on the AC side. So that is why we make this division. And also for measurement of DC link, we have internal measurement of this DC link voltage source, and we can use a multimeter to get this measurement signal. Also, because everything in the reference values is in per unit, we need to divide the DC link voltage by the base value to have it in per unit. Now let's run the updated model for a different values of DC link voltage. If we set the voltage to 0.5 per unit, we can see the generated voltage is around 0.5 per unit, and that is because we have the division of the reference voltages by the DC link voltage, which in this case leads to 2 per unit, but then we have the saturation block as well. That is why it doesn't reach to the 1 per unit, because the modulation index is saturated and DC link voltage is 0.5 per unit. That is why we don't get the 1 per unit there. Actually, this division is there to compensate for the small deviations of DC link voltage around the nominal value. For example, if you test it for 1000 also, you can see that it's not working properly because the division makes the modulation index very small and the DC link voltage is also very large, which is not realistic. But if we consider the around the nominal value, even up to 2 per unit, we can see the impact of DC link on the output AC voltage is compensated, especially for 1.1 per unit. To make sure we can disconnect this division by DC link voltage and run the model for a DC link voltage of 1.1 per unit and see that the output voltage is also 1.1 per unit. While if we consider the impact of DC link voltage, we can see that the output voltage is 1 per unit. At the end, we are asked to set the DC link voltage to 1 per unit and run the model for different values of reference voltages. Since we have this modulation index subsystem for saturating the modulation index, the resultant output voltage is expected, and for high values of the reference voltage, it remains constant and doesn't change and doesn't enter the nonlinear area of the converter. In the homework section, we are asked to add this modulation subsystem to the model that we have from module 2. So to further develop this model, you need to add it here before the DQ to ABC transformation. For the DC link voltage, either you can use the internal measurement of DC voltage source in combination with multimeters to get the DC link voltage and give it to the modulation index block. Also, you can use the voltage measurement block and connect it across the DC link to get the DC link voltage. In the second part of the homework, you are asked to search in the model and see the scaling factors for transformation. Where are they used? Are they used in a proper way, and so on? And what if we don't use the proper scaling? What is the impact on the output generated power or other signals? One thing that I really recommend you to do is try to answer this part by drawing the power control loop or the overall control diagram of the model. That really helps you to understand the model in very detail, which will be helpful in future exercises and also for your understanding of the model for the future use or for any other course that you might use the model. And this is the end of exercise of module 5.